Hello. In our last session, we talked about rational inequations and we observed that every rational inequation has rational function in it. And I also mentioned that critical points of rational functions do matter to us. They would play an important role in the solution of given rational inequation. So let us continue with how to solve rational inequations. One method what we use to solve rational inequations is method of intervals, and that method of intervals is based on the critical points. Now before I formally introduce you method of intervals, let us take one small example and just stretch our mind that how perhaps this method would work. I take suppose x minus 1 upon x minus 5 less than 0. Then of course, x minus 1 upon x minus 5 is of the form px upon qx. And then, as I said before, that we need critical points of numerator, that is x minus 1, and of the denominator, that is x minus 5. And then how do we find critical points? They are nothing but zeros of the polynomial. So, x minus 1, this polynomial's critical point would be x equal to 1, and x minus 5 critical point would be x equal to 5. So we have here x equal to 1 and x equal to 5, the critical points. Now, the moment I get x equal to 1 and x equal to 5 as critical points, what next step I would do? Obviously, I would think that do they satisfy? Now, x equal to 1 and x equal to 5 do not satisfy. Obviously, x equal to 5 was anyway not expected. But x equal to 1 does not satisfy because it is a strict inequation. Now, next step could be that I would try to plot x equal to 1 and x equal to 5. The moment I plot x equal to 1 and x equal to 5, we are dividing the entire number line into three parts. One region less than 1, another region between 1 and 5, and last region would be 5 to infinity kind of. So, and we have already declared that x equal to 1 and x equal to 5 do not participate in the solution set. So, my next attempt would be that interval wise I check those sub intervals what we have made, minus infinity to 1, then 1 to 5 and 5 to infinity. Now in these sub intervals we would check one by one. Now if I take x equal to 0 which falls on the left side of x equal to 1, and I would check that if I substitute x equal to 0, does this point satisfy inequation? And I would find that it turns out to be minus 1 upon minus 5, which is positive, and what we need is actually in the given inequation less than 0. So x equal to 0 does not satisfy. So if this story happens for x equal to 0, then actually it would happen for all the points which are on the left side of 1. So it is not only for x equal to 0. So it happens for all the points on the left of x equal to 1, that those points will not satisfy the inequation. Now if I take a point between 1 and 5, say x equal to 2, and if I substitute, what will I find? 2 minus 1 upon 2 minus 5. And that happens to be 1 upon minus 3, means it is less than 0. So if this has happened for x equal to 2, that x equal to 2 has satisfied the inequation, then it will happen not only for 2, but for all the points between 1 and 5. So we have found that 1 to 5, all the points will satisfy the inequation. Now similar story, I go to next, that last interval, that is 5 to infinity, and I take x equal to 6. Any point you can take, not necessarily 6, you could have taken any value which is more than 5. And then I observe that 6 minus 1 upon 6 minus 5, that is positive. So x equal to 6 does not satisfy inequation. So actually what we have found without knowing any formal method, that the moment I have found critical points, then mark them and try to find which interval points satisfy inequation. So indirectly we are arriving at one particular method, and that method is based on that rational function retains its sign between two critical points. So the entire method of intervals would be based on this. So let us move further. We started with strict inequation and we found that its critical points are not solutions. Now if equation was non-strict, then numerator's critical point would have satisfied inequation. Then we observe that if inequation is non-strict, then critical points of the numerator would participate. Numerator means p and x. If you recall what definition we had given for rational function, we had written Rx equal to Pnx upon Qnx. So if I say numerator, I mean Pnx. So Pnx critical point will be participating in the solution set. Now, if that method is to be applied, then what have we done? Exactly same steps now we will be applying to any question. That first thing is find the critical points, mark them on the number line as they appear. As they appear, when I say, obviously the smaller one on the left side and the bigger one on the right side. Now, by marking this, we have actually divided the number line into finite subintervals. Then, pick up any point from any interval. Not necessarily the leftmost or the rightmost or the middle one. Nothing like that. You can pick up any point from any interval, and then we actually substitute exactly the same method what I did just now. We substitute and check whether the required sign is maintained there or not. If required sign is maintained, then that particular interval will be participating in the solution set. And if we are not finding the same sign, that means the neighboring interval will participate. These are the steps based on which we will be applying method of intervals. Thank you and wait for the next session.